This section is about logarithmic functions. So we started by looking in this unit at exponential functions, and then we looked at inverses, and inverses are functions that can undo what has been done to x. So the logarithmic function kind of comes out of a necessity with those two things combined. We know how to solve an equation where we know what the exponent is. So for example, if I have x squared equals 9, we know that a square root undoes a squared. We get that x equals plus or minus 3. But what if my equation is something more like 3 to the x equals 8. How do I solve for x there? I can't really take an x root because that would be an operation that is undefined. I don't know what x is. So we need an inverse operation to be able to undo essentially being the exponent. We need something that's going to bring down an exponent so that we can work with it. And so that is where the logarithmic function came from. The inverse of an exponential function is a logarithmic function. So if I use an exponential function to evaluate something, I can use a logarithmic function to undo whatever I did there. Now, the definition for logarithms, this is kind of the most important part of what we're going to look at today, is that for all real numbers y and all positive numbers a and x where a cannot be 1, it is always going to be true that the statement y equals log base b of x is equivalent to x equals b to the y power. So remember we talked about with inverses, we switch the x's and y's. You'll notice kind of a reversal of which side things are on there. But here are some important things to help us remember what we are looking at here, okay? B represents the base in both log form and exponential form, okay? Now, when we see that little subscript here with the b, the way you say that out loud is log base b of x. It might be log base 2 of x, log base 9 of x, log base 0.5 of x. So that's the way that you would read that out loud. And then the most important thing here, this is really the key to all of it, is that logs equal exponents. That's the whole point, is they help us find a missing exponent, which is what we have when we have an exponential function. So if I want to find the log base b of x, I can interpret that as the question, when the base is b, what exponent makes the answer x? So for example, if I have the log base 3 of 81 equals 4, I know that that has to equal 4 because, again, it's looking at if the base is 3, what exponent gives me an answer of 81. Since 3 to the 4th power equals 81, the answer to log base 3 of 81 is 4, okay? So let's just practice first switching these back and forth. I'm going to do a couple and have you try some here on your own. So for number 1, we have 4 to the 3rd equals 64. Now these are in exponential form. We want to rewrite them as logarithms. So 4 to the 3rd equals 64. I'm going to start with my log and decide my base. So since the base of this exponential term is 4, we're going to use 4 for the base of the log. Now this is a subnumber. It's kind of like an exponent, but on the bottom. So it's tiny and lower than the rest of the writing. And then, again, the inverse piece is going to switch these two. It's really helpful to remember that logs equal exponents. So that means that the 3 has to go over here, which tells me that the 64 goes inside the logarithm. Now, this is kind of a silly thing, but just to be really clear about how we write these, if you think about like elementary school with your little racetracks here, okay, the log is just like regular handwriting, log like that. The base is dropped down lower and it's smaller. Whatever goes inside the log is also normal size. So that is kind of how you want to think about where the pieces go when you write this stuff out. Okay. Pause the video for a second and see if you can do number 2. Remember to keep the base of the log. Logs equal exponents. And then whatever's left goes inside the log. So take just 2 seconds here to try that. So since our base is m, we're going to do the log base m. And then the exponent and the equal to are going to switch sides. Logs equal exponents. So that means I want n on the inside here. Now for number 3, it's a good idea to think of this in parentheses here. So decide first what's going to be the base of your log. It should be 3, log base 3 of x minus 1 equals the exponent, which is 8. Those parentheses around the x minus 1 are absolutely critical. If I leave them off, log base 3 of x minus 1, then that means we're only doing the log base 3 of x and then subtracting 1 from that. It's not included inside, which is what we want here, okay? Now we can do this in reverse order exactly the same. So if I give you a logarithmic equation, we want to rewrite this in exponential form. So we will always start with the base exactly the same. Now here, the base of the log is 5, so that's going to be the base of my exponent. Now I need to decide what the exponent is, and remember that logs always equal exponents. So the squared will go here, and that will equal 25. And we can see that's a true statement. 5 squared equals 25. Okay, take a second to pause your video and try numbers 5 and 6, and I will come back in 2 seconds with those answers. So you should get 9 to the b equals a, the base is 9, and logs equal the exponent. And then here I should have 7 for the base, 29 for the exponent, equals x minus 3. Now you can leave that in parentheses there if you want or not, because it's just one side of the equation. So that is just fine, okay? We're gonna stop with that part of the video right there, and we'll pick up with the next examples in just a few minutes.